Okay, so this is the fourth part of our tutorial on this application we wrote to visualize loci of triangle centers for triangle families mounted or inscribed in an ellipse. And the difference between mounted and inscribed is going to become clear. So this is our fourth installment. Today we're going to talk about, we're going to do a recap of the first three, and I'm going to cover the idea of locus types. Okay. So let's just do a quick recap, okay? If you recall our application, here's our application, right? I have an ellipse, I have a family of triangles, and I can visualize the locus of a particular triangle center, in this case, the incenter x1. Now, you're going to recall that we went over two dimensions here. I can change the triangle family by going on this menu here, so I can go from billiard, three periodics, to the homothetic Poncelet pair, and there are other pairs here that we haven't actually shown yet. There's this in-circle pair, there's the in-ellipse pair, and so forth and so on. Okay, and another dimension that we showed was the choice of the reference triangle or a derived triangle. So here's a reference triangle shown the dash blue here, and I could say, look, I'm also interested in the anti-complement of the reference triangle, so here it is. And I want to study or visualize the locus of the incenter of the anti-complement or the anti-complementary triangle, not of the reference triangle. I could, for example, be interested in looking at the path of the incenter for the excentral triangle. Here's the excentral triangle, so I can do that. So here's the path of x1, so forth and so on. So as a recap, okay, so here's a close-up of the interface. If I play around with this drop-down, I can choose so-called triangle family or the mount, okay? It's going to become clear why we have these two terms, but they're really triangle families. If I play with this other drop-down combo box here, I can choose the type of triangle, the type of derived triangle. So I can choose between the reference triangle, the excentral triangle, the anti-complementary triangle, the medial triangle, and there's about 30 of them there. Now, I want to talk a little bit about today about this other drop-down box, which has this calligraphic L here on top to the left of it, and it's called. It allows you to select the locus type. Now, before we go there, I just want you to bring this back to memory. The fact that we have actually 4 areas. There's only 3 of them that are identical. Okay, so here's one area shown over here. There's a second identical area down here that allows you to turn on another channel to visualize something simultaneously. There's a third one down here with the exact same controls, and there's a fourth one on the bottom. Okay, so for example, if I was interested in not only visualizing the path of the incenter on this particular triangle family, I might want to turn on the path of, for example, the barycenter, so x2, not for the reference but also for the excentral. So now I can simultaneously visualize the path of the incenter and the barycenter of the excentral family. Okay, so now the subject of this video is the following. I want to show you guys, so you've seen these two controls that allow me to select what particular Kimberling center I want to visualize the locus for. But if you actually drop down on this guy here, there's a bunch of options here. I'm just going to go over a couple of them. Okay, the very first one is the one we're used to. It's called XN. So that allows me to select. So let's reset the UI here. I'm going to reset the UI. I'm going to leave it on XN. And of course, there's an off. I can turn this one off. But if it's turned on, and the first one is always going to be by default turned on, it's going to say, look, you're going to be visualizing the locus of this Kimberling center. Kimberling center number 1, Kimberling center number 2, number 3, number 4. And I can use the scroll bar here to quickly scroll through 1,000 Kimberling centers, the first 1,000 in the list, or I can actually type it in. So I could type in, for example, you know, the Delonchamps point, which is x20, and I would get x20, or I can use these pluses and minuses here, so I can just click on these buttons, or finally, after I click there, I can just use my keyboard, and I'm going to be going through it. Okay, so that's quite handy. Now, what's under this menu here? This allows me to choose the type of, if you want, triangle center or locus type that I'm interested in seeing. I'm just going to go over the next important one, which appears down here, which is V1, V2, and V3. This is actually going to show me the locus of a particular vertex of my triangle family. So let's go ahead and select V1. There's V1. Now remember that this triangle family is inscribed in an ellipse. So if it's inscribed in an ellipse, the locus of V1 is going to be the ellipse. The locus of V2 is also going to be an ellipse. It's another vertex of this triangle family. And it's showing me here that this locus is an ellipse. Okay, so if I switch forward to, for example, the homothetic pair, this is also triangle family inscribed in an ellipse, so the locus of one of its vertices is going to be the ellipse. Now let's go back to the billiard over here. Okay, I'm going to stop this motion here for a second, and I'm going to say, okay, I don't want to visualize V2, or let's go back to V1, which is more default. There's V1. I don't want to visualize V1 of ellipse-inscribed family because I know that locus is the ellipse. I want to visualize the locus, for example, of the anti-complementary triangle. So let's go ahead and click here. There's anti-complementary triangle. It's shown here. And now I'm visualizing the locus, which is a non-elliptic beast, and I can exacerbate that a bit by making my ellipse, the original ellipse, be more eccentric. I can visualize the locus of V1. So you get this sort of dumbbell or hot dog kind of thing. Squeeze the hot dog, squeeze in 2 points. And you can see that the locus of vertices of the anti-complementary triangle are non-elliptical. Let's visualize the locus of, say, the excentral triangle. Here's the excentral triangle. What's the locus? Let's reduce A over B so this thing becomes smaller. What's the locus of the vertices of the excentral triangle, or of the so-called excenters, right? That locus happens to be an ellipse. Okay, and this is a result that we've been aware of. I think we have a publication where this is proved. Okay, so that's the locus of a vertex of a derived triangle. Okay, so you can select any derived triangle you want. You can select, let's take, for example, here, the orthic triangle. Here's the locus of a vertex of the orthic triangle. Now, this is a pretty interesting curve. It has 2 self-intersections, one over here, another one down here, and you have these 2 internal loops. Now, because this family is actually cyclical and it's inscribed in the ellipse, it doesn't matter. If I switch the vertex that I'm visualizing to V2, I'm going to get the same path. And if I switch it to V3, I'm going to get the same path. Okay, so this is a good tie-in with the next subject. So we've been talking about this difference, right, between a triangle family and this label here, mount. And why is this application called ellipse mount? We call this thing, right, the name of our title here, our title is Loci of Centers of Ellipse Mounted Triangles. Why not ellipse inscribed? Because about half of the triangle families that we've been making available are these Poncelet ellipse inscribed families. So I have here the billiard family. Let's reset it. I have the billiard family. I have this homothetic family, also interscribed between 2 ellipses. I have this encircle family. This one is interscribed between an outer ellipse and an inner concentric circle. You can see here that the encircle or the incenter of this family is automatically stationary. And I have other families. I have one that is the opposite. I have the outer conic is a circle, and the inner one, the inner Poncelet conic, is a concentric ellipse. Now my x1 is not stationary. What's stationary in this family is the circumcenter of the family, stationary. And so, you know, we make available a few of these families, and the ones that are Poncelet and that are ellipse inscribed are marked here with these little stars. Now, after the last one, this Brocard family, you have a sequence of other families here that are not ellipse inscribed, they're ellipse mounted. And actually, this is how this whole little exploration began. So we started, for example, with a family. Let's select major here. What's the major family? The major family is when you mount 2 vertices of a triangle family on 2 fixed locations. You're going to mount them or affix them with respect to the ellipse in a fixed manner. Okay, so in this particular mounting here, this major mounting, I'm mounting a first vertex on the left vertex of the ellipse and a second vertex of my triangle family on the right vertex of the ellipse. And I'm going to let the third vertex move freely across the boundary of the ellipse. So let's watch that. And I'm simultaneously plotting, in this case, the circumcenter of this ellipse. Okay, now we do know that the circumcenter of a triangle is the intersection point of the three perpendicular bisectors. So since one of these sides is actually pinned in this manner, this x3 is going to have to be going through, it's going to have to lie on one of the perpendicular bisectors. And since one of the perpendicular bisectors is a fixed line, you get this kind of effect, right? But of course, I can observe. So here you're seeing the symbol L for the first time. Okay, so numerically, the system is indicating to us that the locus of this guy is a line. There's an L over here as well, right? And there's an L over there. Now let's look simultaneously at the same thing, at the same family, but I'm going to choose major here again as the same triangle family. And I'm going to leave it as an incenter, and I'm going to select XN. Okay, now let's look at those simultaneously. Here's the locus of the incenter, and here's the locus of the circumcenter. Let's go ahead and change that family to a related one. Instead of actually affixing these two vertices to the left and right vertex of the ellipse, I'm going to affix them to the foci. So I'm going to change this mount here to foci mount. So focus mount, FS. It's identified by this letter FS. And look at what happens. Okay, nothing happened to x3. It continues to go through its line, right? However, and it's actually, I believe it crosses through infinity, so it comes back the other way, right? However, the locus of x1 has become an ellipse. Okay, so if you have a focus-mounted triangle family, the locus of the incenter is the ellipse. Okay, and I can actually select this tandem setting here. I'm just going to check the mount tandem setting. So if I change the mount now from focus to go back to major, both of them are going to change simultaneously. So I go back to that other case. Now the locus of x3 is finite, and the locus of x1 is no longer an ellipse. Okay, but I actually wanted to show you guys this sort of ellipse-mounted family of triangles because I want to relate to what we were doing before, which was to observe the locus of a vertex, right? So remember that we were observing the locus of a vertex. I actually set this guy to V1, and I was observing the locus of a vertex. Now, because V1 is inscribed on the ellipse, right? The whole family is inscribed on the ellipse. I'm going to get the same phenomenon here. Now, let's go ahead and instead of using the reference triangle, I'm going to switch back to the anti-complementary triangle. So here's the anti-complementary. Let's turn off the x1 because we don't need it anymore. Now let's follow the locus of V1. Okay, now this particular V1 is precisely the vertex that is, let's say, antipodal to one of the vertices on the family. So if it is antipodal with respect to the center of the ellipse, it's also going to lie on the ellipse. So the locus of V1 is the ellipse itself. Now let's select the locus of V2, which seems to be outside of the ellipse. Select the vertex V2. So I go here and I select V2. And look at what I get. The locus of V2 is another ellipse. It seems to be a perfect copy of the original one. So if I play around with the original one, I get a vertex of V2. So you start getting a lot of properties when you start analyzing, and some of them are not trivial at all. But we're now looking at the locus of one of the vertices of the anti-complementary triangle for this particular family, where two of the fixed vertices are on the vertices of the original ellipse. What happens if I switch those two vertices to the foci? Let's go back. I'm going to go back to foci mount. So now my family is foci mount. What happens? Because the anti-complementary triangle is homothetic to the original one, I also get a copy of the original ellipse, and it looks like one of the foci of this original ellipse is probably it probably coincides with the focus of the original one. So this is actually pretty cool, and I can of course change A over B to observe this phenomenon, and it's pretty cool. I'm looking at the locus of V2 of the family of anti-complementary triangles. So now let's go ahead and take a look at V1 again, but not of the anti-complementary, but of the excentral triangle. So let's take the excentral triangle. Recall the excentral triangle has sides which are perpendicular to the bisectors of the original triangle. So you intersect those, and they pass through each vertex, and their directions are perpendicular. So interestingly, for this particular case, if I track, and let's go ahead and rotate that. I'm going to show you guys this really neat control here. I can rotate this whole picture by 90 degrees, so it fits better in the aspect ratio of a typical displays, right? So I have that original ellipse, now this white ellipse rotated 90 degrees. Here's my family. The family has two vertices affixed to the foci and a third one that is sliding on the ellipse. Look at what's happening to one of the vertices of the excentral triangle to this family. Well, it's actually going to an ellipse. I can see an E here. And then the cool thing would be for us to derive what this ellipse is. Apparently there's a paper by 2006 I'm going to put on the comments that has shown this result back in 2006, 14 years ago. This is pretty neat. Now you may ask yourself, what's going on with the other three vertices? Are they doing the same thing? Are they moving around the same ellipse? So let's go ahead and open them up here. I'm going to go ahead and put V1 on the second channel. I'm interested in the excentral triangle, and I don't want to look at V1, I want to look at V2. What's V2 doing? Okay. So V2 is actually flowing through a straight line, and this is an infinite straight line. I can zoom out as much as I want, and V2 is going to go through infinity and come back on the other side. Okay? So the second vertex of the excentral family of these focus mounted triangles it lies on a straight line that is tangent at one of the side vertices of the original ellipse, major vertices, and it's just horizontal. Let's do the same with the V3 vertex. So I'm going to open it up here, V3. I'm going to say I want to look at the excentral, and this guy's focus mounted. So by symmetry, V3 is also moving along its own line. This yellow line here, it's tangent to the top of the ellipse. And you get this, I would say, pretty pleasing to the eye phenomenon, right? We start with a pretty simple thing, right? We start with an ellipse, the white ellipse. Then we define a triangle family that has two vertices fixed on its foci and a third one which slides over the ellipse. And then we say, okay, what's the locus of a first vertex of the excentral triangle, a second vertex, and a third one? And we get one that is an ellipse and two that are lines tangent to the original ellipse. What happens if I switch from focus-mounted triangles to major-mounted triangles? So I'm going to mount them on the up and top, so left and right, because this thing is turned around for 90 degrees. I'm going to mount them on two major vertices. So now my family is slightly different. You see the foci over here. The family is slightly different, and you get a slightly different phenomenon. So let's look at that phenomenon. So V1 is moving on something that has two kinks. They're all moving along actually the same curve, it looks like it, right? Yeah, so in this particular configuration, the three vertices become cyclical along the same curve. You can ignore this straight line here. This is an artifact of the way these loci are being calculated. And V1, V2, and V3 are assigned. That straight horizontal line doesn't exist. So look at what happened, right? Just by going from a focus mount, which gives me this beautiful result, an ellipse and two straight lines, to the major mount, I get that. Let's go to the billiard mount, or the billiard family. What happens in the billiard family? In the billiard family, if you recall what we talked about before, the three vertices are cyclical and they move along an ellipse. How about the homothetic mount? You don't get an ellipse. You get something that is non-elliptical for the three vertices. If I go to a proper mount and not a Poncelet family, just recapping, major mount doesn't give me something that looks simple, right? It has these two cusps or kinks. I don't know if this curve is regular or not. I can try to study this, right, by changing the A over B. If I go to a focus mount, I get this other phenomenon. What if I go to a minor mount? So the minor mount is the opposite of the major mount. Let's go ahead and turn this back to 0 so we can look at the ellipse as it is. What is the minor mount? The minor mount is when I affix the two vertices of the triangle family not to the left and right vertices of the ellipse, but to its co-vertices, meaning the top and bottom ones. So let's observe that, what happens to that family. So now I have three vertices that are, let's ignore again these horizontal lines. They're artifacts of the way V1, V2, and V3 are assigned. There are these discontinuous jumps that don't exist in the actual locus. The locus is a continuous butterfly-shaped curve. It's not elliptic, obviously, and you can sort of distort it, right? There's going to be a couple of interesting points. I always like to ask this question, what is the A over B for which something interesting like this happens. For example, the locus touches that vertex. So it looks like it's something close to square root of 3. Maybe it is square root of 3. Okay? How about this other point here where the locus goes through the focus? I'm getting another A over B over here, and so forth and so on. I can keep going here, and it looks like I can never make this guy touch the center, but I have these two interesting or critical points. I go through the foci, or I go through the vertices. Okay, so so I guess now you guys have the 3 major dimensions of this simulation or this application environment. Just recapping, the first one is the choice of triangle family, be it a non-starred mounted triangle family where V1 and V2 are stationary and V3 is going through the ellipse. You also can choose these starred Poncelet families here. Okay, so I'm now on the minor mount. We also know about the second dimension of this, which is a choice of the particular triangle I'm going to be observing, be it an anti-complementary, an excentral, an orthic, so forth and so on. And now I have this third dimension, which is what kind of a locus am I going to be observing? Am I going to be observing vertex loci, V1, V2, V3, or am I going to be observing a Kimberling center, triangle center loci? Okay, so I guess that's what I wanted to cover, and I'll see you on the next video. I hope you enjoyed it.